Hello, my name is Ignacio Erazo, and I'm going to present about submodular dispatching. First, I'm going to talk about the problem definition and some real-world applications, and afterwards, I will talk about the IP model we propose. This is joint work with my advisor, Alejandro Torriero. So, we have a set of end customers that must be served, and our goal is to minimize the makespan while we do it. So, each customer has a release date, and which means that any route serving them must leave the depot after that time. Also, we have one vehicle and it's uncapacitated. So the vehicle can serve all clients at the same time if needed. A submodular function F establishes the route costs, and it's also a monotone function, and it has a value of 0 if no customer is being served. So why is this useful? This is useful because it has multiple applications in real life. So we're going to focus in this presentation on same-day delivery, which is useful for e-commerce, and it's a very important topic nowadays, as we can see in the figure to the right, because most of the big brands are offering this service. But it's also useful for the order picking problem, which may be using warehouses with very long aisles, but also machine scheduling and routing trees, among others. So we propose an IP model, and it relies on the fact that we don't really need more than n dispatches to be made to get an optimal solution. So we have two types of variables. First, the variables x, I, s, which are binary, and have the value of 1 if the dispatch number I has the customer set S as root, and 0 otherwise. So we actually only need to make one variable for each subset S, so we have 2 to the n variables, which is quite a bit. And the other types of variables are the variables TI, which are the time at which the dispatch number I leaves, and the makespan, which is Tn plus 1. So this is our P model, and the first constraint is actually just minimizing the makespan. The second is that we have to each dispatch must leave at the time or after the release date of that specific customer. Also, constraint number 3 is very important because it means that we have to take into account the cost of each activated route to compute the departing time of the next dispatch. And it helps us just to get the correct value on the makespan. Constraint number 4 is just a coverage constraint, which means that each customer must be served, and it's without loss of generality putting equal to 1 because the function, the modular function is monotone. So we don't really need to serve any customer more than once. Finally, we have non-negativity and binary constraints. So how do we even solve this problem? This problem is strongly NP-hard, even for simple graphs like the star graph that we can see in the figure. So as this problem is very hard because we saw that it has an exponential number of variables, we propose a dynamic program based on the idea of serving the customers in a first in, first out manner. And that's done just by ordering the customers according to their release time. We prove that this algorithm is actually a tied to approximation. We also characterize the FIFO optimal functions, which are just a set of functions that have an optimal solution given by this algorithm. So let's talk about an SDT application. This is tactical design. As we can see in the figure in the left, we have a part of the Metro Atlanta area, Chambly in particular, and we have these blue dots, which are just like centroids of orders, arrivals, people. This information was pulled out of a previous paper. And basically what we did was to do a continuous time approximation on all of these arrivals, such as to get a function that is representative of the routing costs for orders in this area. This function happens to be actually a submodular function, just like the one we needed. And it has it's actually dependent on the cardinality of the number of orders. This function we prove is FIFO optimal. So we can use our algorithm to get the optimal solution. Basically, we use different sets of error rates, such as to see what happened to the optimal solution. And this helps us to plan ahead and improve our operations, such as to get a better SDD service. Finally, I want to thank you for listening.